Welcome back. So we're on page 173 and we're looking at quadrilaterals. So before I define a quadrilateral, we're going to recap that we name points in geometry with capital letters. That if we join two points together, we create the line AB. Let me switch over to pen here. We create the line AB that goes on forever, and we can define a line segment CD, which is defined like this, and the measure length of CD is defined like this. The distance, in other words, from C to D. Distance is inherently positive, it cannot be negative. And if we have 3 points with a ray emanating from a vertex, we make an angle. Okay, so an angle is in a little bit of a way like a three-sided figure, but it's just, or it uses 3 non-collinear points, 3 non-collinear points to define it, and it is an open figure. There is the inside of the angle and there is the outside of the angle, but it's wide open, there's no closing to it. So if we decide to close an angle, we get a triangle. Or if we use 3 lengths, 3 straight edges called laterals, if they were all equal, we would call it an equilateral triangle. Equilateral triangle. And just to flick back and check our spelling there, a few sections ago we came across the equilateral triangle. In this section here, I think here, equilateral triangle. Okay, so the next thing up from an equilateral triangle is a quadrilateral, and I brought you back to this idea here because of the word lateral. Okay, so in a way you could say a triangle is a trilateral in the way that a quadrilateral is just the next logical thing up from a triangle. So it has 4 sides. Okay, and of course it can be very random after that. As long as you have 4 sides, you can get a quadrilateral. In particular, just like for triangles where we study right angle triangles, acute triangles, obtuse triangles, isosceles triangles, just as we do in triangles, we're going to be looking at lots of different types of quadrilateral. Okay. So the first quadrilateral we look at here is a parallelogram. Okay, and while there are several ways to define a parallelogram, one thing that it has, one way of saying it is that it has a pair, opposite sides are parallel, and then we can go with further opposite sides at any particular angle. So just look at what I'm going to do here. I'm going to come across here at an angle and just slide this and make a parallel, parallel transversal if you like, because this transverses across between the 2 parallels, and so does this. So and these are parallel as well, and to show that these are parallel I've used up the single arrow, so I would need a double arrow there. Okay, so what are the properties of a parallelogram? Opposite sides are parallel. Okay, so let's just name the sides. We might be more inclined to name the points A, B, C, and D. Okay, so we will say line AB is parallel to line DC. Now you try and write the other one, pause the video and say that these are parallel. Okay, you would have said that AD is parallel with BC. Okay. Furthermore, opposite sides are equal in length, so the AB distance AB is equal to distance DC, and distance AD is equal to distance BC. Okay, the angle at D is equal to the angle at B, so I'm just going to say angle D, assuming the assumption is that they're internal, is equal to angle B. So opposite angles are equal. Okay, these are opposite angles and they're equal, and the other two opposite angles would also be equal. So we would have that angle A is equal to angle C. Okay, now we're going to draw in one diagonal and see what it looks like. Okay, so let's just draw in one diagonal. So what does that generate? It generates diagonal angles here and here. Okay, and those diagonal angles are equal because they're alternate angles. The diagonal itself is a transversal, and then you have your parallel lines, so these are definitely equal. Okay, furthermore, these angles here are equal, but they're not equal to each other. That only happens in a rhombus. Okay, so that which is when it's a parallelogram with all four sides equal. So we stick to our guns here now and say that sure enough opposites are equal, and there's the alternate diagonal angles are equal. Let's write that down. Alternate diagonal angles are equal. There's lots of other stuff going on here, so before I move on to looking at before I move on to creating another diagonal and bisecting, we have two triangles here, and they're congruent, they're the same shape, they're just twisted around. Okay, and now I'm going to draw in the second diagonal. Okay, now if we check, draw a big circle here, and if we check carefully, it goes through A and it goes through C. Okay, so the diagonal here has been bisected. We might call that a major diagonal, and this diagonal has also been bisected, so we could have a smaller circle there. And if you ever see a question with circles, you'll say, oh, I've seen that before. Okay, so you have a minor circle and a major circle, and you have a minor diagonal and a major diagonal, depending on which one's going where. Okay, of course that creates angles, and these two angles will be equal because they are vertically opposites, as will these because they're vertically opposite. Furthermore, if we go back to the original, let me just draw one here, just sketch it, but assume this is a parallelogram, that this angle and this angle together, these two form 180 degrees. They're supplementary, they're the same as a straight edge. Okay, so we say that adjacent, which means beside, adjacent angles in a parallelogram are supplementary. meaning if we go back to original, angle A plus D, the measure of angle A and D is equal to 180 degrees. Okay, sorry I went off picture there. So adjacent angles in a parallelogram are supplementary, and A and D equals 180 degrees. That's pretty much everything you need to know about a parallelogram. They're very, very interesting. Even more interesting is a rhombus down here. And we're going to learn how to draw a rhombus because it's so important. So to draw a rhombus, we will need a working line and a compass. Okay, so let's just define a vertex there by marking a point. Take your compass and open it out a certain amount. Okay, and draw an arc. Now let's just well let's come over here now and draw another arc out this way. Okay, and come up here and draw your last arc. Okay, so it got a bit messy there for a minute, but let's think about what we've done. Let's take this point, this point, this point, and this point. Right, so we know that all these sides that I'm drawing are equal in length. That one there, this one here, because they're all based on the same compass opening. Okay, so this is a rhombus that we've constructed, and it's very, very important because it's also a 60-degree rhombus because it's behind nearly all the constructions we'll be doing in a different chapter. Okay, so let's just draw in the diagonals and see if there's anything special going on here. You should do this for yourself as well. So, is there anything special this time about the intersection angles? And there is. They're 90 degrees. Okay, they're all 90 degrees. Okay, so the angles of a rhombus bisect each other at 90 degrees. And that makes it very special. Okay, not only that, we have that this is equal to this because it's a parallelogram, but it's also equal to this because this is an isosceles triangle. Okay, so the diagonal angles in a rhombus are all equal to each other, not just alternate ones like they were in the parallelogram. So that's really interesting. Okay, so if you straighten up a parallelogram, you get a rectangle, and the definition of a rectangle is a quadrilateral with 4 right angles. If you turn a rhombus into having right angles, you get a square, and that's pretty much it. Okay, there are a parallelogram. A rhombus is a parallelogram, so you kind of have a kind of a Russian dolls type of compass in terms of shapes. Okay, where we can say that a square is a rhombus. So every rhombus, the set of rhombuses includes all the squares. The set of parallelograms contains all rhombuses and all squares, and somewhere in there we'll have rectangles. And then another very important shape that we'll be dealing with on the course and in exams is the trapezium. Okay, so before we go on to we'll talk about that in a second, but the trapezium is very important too. And with the trapezium, we just want, instead of like a parallelogram where both pairs of opposites are parallel, in the case of a trapezium, it's only one pair of opposites are parallel. But it does create some very interesting properties. One of which is that we still have the diagonal creating alternate angles because this is still a transversal, and we have very interesting points too in terms of that the area of this is equal to the area of this, even though the shapes can be quite different. they're still of the same area because they have the same base by perpendicular height. Okay, let's try and stick to the book. So other angles in a quadrilateral, well, just that proof there, in any quadrilateral we can very quickly prove, so any quadrilateral at all, a random quadrilateral, if we put in one diagonal we create two triangles. There's 180 degrees in each triangle, and so all of the angles, because these two would add together like you have here, will add up to 360 degrees. So the internal angles collectively add up to 360 degrees. And I've already dealt with this here. Okay, in a square, well actually, yeah, in a square, in a square the diagonals bisect each other, and they're equal in length and they're all at right angles. In a rectangle, all diagonals bisect each other into four congruent line segments, all four the same, and so on. And we've dealt with all that. So we'll go on to example 1, and I'll try and do it independently of the solution in the book, through a process called problem solving. So what we always want to do is to reconstruct the examples for ourselves. Okay, so let's do that by drawing this. Okay, now it doesn't have to be an absolutely perfect drawing, so what I'm going to do is a really handy tip to draw a longish kind of parallelogram is to take your two working lines, in other words it doesn't matter if they extend, and then take a kind of a fatter pair of transversals. So we have this, drawn this in. It doesn't have to be exactly 28 degrees, I can just model it like that. So it's a sketch. Okay, now let's see what they're asking us. So I've reproduced the quadrilateral or the parallelogram A, B, C and D. So let's get our problem solving using the theory we know. Let's put it to the test to find the angle from B to C to D, the size of the angle from B to C to D. From B to C to D, to find this angle. Okay, so the hardest thing about it is probably writing it down. From B to C to D. The size of that angle is, well, opposites are equal, so it's 115 degrees. Okay, y opposite angle property. Okay, the other thing we need to find is the angle from B to D to C. Oh no, 1, 2, find the angle from A to B to D, from A to B to D. Okay, this angle here. Okay, but we start looking at it and studying it and say, hang on, we know this is 28, and sure, they're alternate angles, so we know that this is 28 degrees, and the reason is alternate angles. So that's your justification when they ask you for it. It's alternate to 28. Now on to 3. Find the angle from A to D to C. Where the hell is that? A to D to C. It's this angle here. Okay, now have it. Okay, we know, and it took me a while there to think about it, we know this is 28. Okay, and we know this is 115, so the third angle in this triangle can be calculated using the angles of a triangle, which is 180 degrees minus 115 minus 28. Okay, 180 is the internal angles of a triangle, minus 115 minus 28 leaves us with the third angle equal to 37 degrees. Okay, and the reason is, and that's 3 angle ADC equals 37 degrees, and the justification or the reason is sum of angles in a triangle add to 180 degrees. Finally, the angle DBC, this angle here, well, that's 37 as well because it's alternate to the one we just got. Okay, so part 4, angle DBC equals 37 degrees. So let's see how we got on. They have 115, they have 28, they have 65 AD. Oh, it was ADC, which made this collectively 65, just as 28 and that. Okay, I hope you understand that. I'm not going to do it again, we'll just drive on. Okay, and then they show the whole triangle there. That brings us on to problem solving, which I am going to do in a separate video. So as always, students, I will see you in the next one.